In this lecture, we're going to discuss how acids and bases actually form equilibria as well. Before, when we talked about strong acids versus weak acids, we talked about how much they dissociate. So, if we actually, let's say we have 1 molar hydrochloric acid. Hydrochloric acid is a strong acid. Hydrofluoric acid is a weak acid. So let's say the positive ion is, this is our positive ion, the open circle, and the filled-in circle is our halogen chloride. And each one of these represents 0.1 mole of each. Same here. So if we have a 1 molar solution, let me just draw 1 liter of it. Let's say we have a container with 1 liter of 1 molar HCl. And let's compare that to 1 liter of 1 molar HF. So identical volumes. So, and this is what we talked about before when we talked about acids and bases, and I said we'd revisit it. So, if each one of these things represents 0.1 moles of each, we'll have 20 particles in there, 10 HCl particles, 10 of each positive ions and negative ions. Same here. In the HCl, I'm going to pause. If we compare these two solutions, HCl there is actually no aqueous hydrochloric acid together. They all break up. So that's what we call the dissociation equation. And we use this in KSP as well, where HCl aqueous breaks up into H plus aqueous plus Cl minus aqueous completely. So let's do the dissociation equation for HF. So it's pretty much the same thing. And what we see is, interestingly enough, that with a weak acid, we form an equilibrium. So in this, with hydrofluoric acid, the weak acid, we have both forward reaction happening and a reverse reaction happening. And the reason why that is that's because the conjugate base of a weak acid is actually a base, whereas that's not true with Cl, chloride. Fluoride is a weak base, chloride is not. So if we think about this in terms of equilibrium constant, so HCl has a high Ka. Ka is just an equilibrium constant for this reaction. So if we could draw the K for this reaction, well, we'd have the concentration of H plus times the concentration of Cl minus all over the concentration of HCl. And this high Ka means that we heavily favor the forward reaction, whereas the Ka for HF has a Ka equal to 7.1 times 10 to the negative 4. So if we call this the equilibrium constant, it works the same exact way as every other equilibrium constant. It's just the equilibrium constant for this reaction, the reaction of the dissociation of the acids. So the ratio Ka is equal to H plus times F minus all over the concentration of HF. Now we can see, since the reverse reaction happens here, that we're going to still have some HF. So that's why the Ka is much lower. So, and what this means is that most of our, essentially all of our HCl dissolved is 100% ionized. So, what that means is HCl aqueous is essentially doesn't exist. It really is all H plus aqueous plus and Cl minus aqueous. And we can actually calculate how much, because we heavily favor our forward reaction. Because of this, we never form an equilibrium. Equilibrium is not established. With strong acids and bases. We're all products. That high Ka. So a large Ka, it means we have a very high amount of hydrogen ions and chloride, the products, versus in a very low amount of that. So we can tell that there. And from this, we can also say that the conjugate base, if you don't remember what that is, go back and look that up in your notes. The conjugate base of HCl, well, the conjugate base being Cl minus, is not a base. Meaning it cannot accept a proton. Which is good, because then our oceans, if you think about it, there's a lot of chloride. And if chloride could accept protons, then, well, our oceans would be very basic. Probably too basic for us to go swimming in. So, moving on. So, most of AHF is actually not dissolved. We have this relatively low concentration of dissolved ions. So most of it is in the HF. It kind of stores it. So it's not dissociated. So most HF we see are together still when we look up here in solution. So the HFs are together. So our free hydrogens are much lower. So, and there's a lot of different things about that. So you can actually calculate this since we know the equilibrium constant. And you're just using a Wright's diagram. So if we want to know how much HF is ionized, we set up our Rice diagram. So essentially I want to know how much becomes ions. So we write our reaction. Let's say in this 1 molar solution. So let's say, assuming we start with 1 molar hydrofluoric acid and none of it's ionized, it's how much are we going to have in equilibrium? Well, we do this just like any other Rice diagram. Use our coefficients to figure out our values of change, and then use our equilibrium values and plug it into the Ka. So our equilibrium is 1 minus x, and here it's x, here it's x. And we can just set our Ka. We know our Ka right here, and we know our value of it right here. We know our equation and our value. So we set it our equilibrium value, and that would be 7.1 times 10 to the negative 4th is equal to x times x all over 1.0 minus x. And we solve for that. You guys can use your solver, or this is a quadratic. You can use the quadratic equation if you want. and you get X is equal to 0.026 moles per liter. So that's our X value. That means that out of one molarity, at 1 mole per liter, 2.026 moles will be dissolved. We can figure out what percentage that is, and we get 2.6%. So only 26 out of every 1,000 HF particles in aqueous solution in a 1 molar solution will actually be dissolved. And so my diagram's a little bit off. But let's move on, and I'll show you how else we can apply this and other applications of it. We'll move on in just a second. So let's say we want to compare the pH of the different solutions here. So let's compare the pH of a 0.20 molar HCl solution to a 0.20 molar HF solution. Now remember, let's go back way back when. Remember, our pH is defined as the negative log of the value of free hydrogen ions in concentration. And this is what we need this at equilibrium. So similar to what we did before, let's calculate our hydrogen ion concentration at equilibrium for 0.2 molar HF solution using a Rice diagram. HF is at equilibrium with H plus, aqueous, plus F minus, aqueous. 0.20 molar to start off for HF is nothing for hydrogen and fluoride ions. So we're going to subtract X plus X plus X, 0.2 minus X at equilibrium. Remember, if our initial is 0.2, we subtract X, what do I get? I get 0.2 minus X. If I start with 0 and I add X, well, I must have X. So we can use our Ka expression. Ka is equal to concentration of H plus times concentration of F minus all over concentration of HF at equilibrium. Remember, we talked about this. If you have trouble, you can go back to your equilibrium notes 2 or 3, I think, is when we covered this. So we can just plug in our values. We remember from before our Ka for HF, 7.1 times 10 to the negative 4. Now that will vary with different weak acids. So we can say our 7.1 times 10 to the negative 4th is equal to X, our values at equilibrium, over 0.20 minus X. And you can solve for this any way you like. You can use the quadratic equation, or you can just plug it into your solver, and we'll get that X is equal to 0.0116. So our pH, remember, is equal to the negative log of our concentration of H plus here. So right here, we can get that, and that is the negative log 0.0116, and that is going to be 1.94. Now, since this is a weak acid, it's going to be definitely closer to neutral compared to a strong acid. So compared to 0.20 molar HCl, which is a strong acid, we can calculate that pH. Well, essentially this, in a strong acid, the concentration of H plus is the concentration of the acid. Think the Ka approaching infinity, and that would mean you'd have approximately 0 HCl left involved in solution. So, strong acid heavily favored the Forder reaction. So, just keep that in mind, the reason why. So, the negative log of 0.20 So strong acid concentration of H plus is equal to the concentration of HCl. The negative log of this is going to be 0.70. So clearly, the pH of the strong acid is lower, meaning lower pH is more acidic than the pH of a weak acid at the same molarity. And temperature and other different things affect that. So that's it for the weak acid 1 notes. We'll start talking a little bit more about later.